Now the term osmosis, I'm sure you've heard before, and I'm sure you've worked with it before, especially since you've taken a biology class. So you already know you're going to move water. And you're going to move that water from an area of low concentration of non-penetrating particles to an area of high concentration of non-penetrating particles. Anybody feel confused? Because we just spent a lot of time talking about things like to go from an area of high to low, but now we're talking about going the opposite direction. Well, let's draw it out and actually talk about it, and I think it might make more sense that way. Okay, so before we get into moving water, let's review some things about how molecules like to move and start with a beaker. And so we'll have a nice big beaker here on our piece of paper, and we'll put a membrane right through the center of it. We'll have side A and we'll have side B. And then we're going to put in a solution. And for it to be a solution, we need more than just water. We need our solutes, so here's our solutes. Alright, so based on laws of diffusion, you know that side A has a higher concentration than side B, so we're going to want to move that solute to side B. Now it's equilibrium. Everybody's happy, everybody has the same amount of space. Great. Awesome. If they can. These things are huge. They're not getting across that membrane. So side A has a higher concentration than side B. And since they can't cross the membrane, these are what I mean by non-penetrating solutes. So we're going to have side B have a low concentration of non-penetrating particles, and side A will have a high concentration of non-penetrating particles. So is that it? They're just going to have different concentrations on the two sides? Well, we already talked about we like to hit equilibrium, so we got to move something. And if we can't move the solute, then let's move the water. Now, who are we going to take the water to? Well, take the water from B, put it over to A, right? Because we talked about we're going to move water from a low concentration of non-penetrating particles to a high concentration of non-penetrating particles. So when water goes from B to A, the water level on side A will rise, and the water level on side B will lower. So now all of the molecules have about the same amount of space. We've hit equilibrium by moving the water. That's what we're dealing with osmosis. So the easiest way I look at this is I say, look at who's crowded, give them water. And so once you can find where the higher concentration is, you just want to dilute it. Okay, so let's talk about some scenarios. Okay, so let's work with 3 beakers, and inside of those beakers we're going to have a solution and a cell. And so let's draw those in here. Now remember, in the inside of all of the cells, we're going to have the basic concentration. So we memorize that as 0.3 osmoles per liter. So go ahead and put that in all of them. And then we can put in our solution. And so there's going to be 3 scenarios I want us to focus on. And right now we're just focused on non-penetrating solutes. So all the red stuff are going to be non-penetrating particles. And so out here on this first one, the extracellular concentration is going to be 0.3 osmoles per liter. So it'll be the same as the inside of our cell. Our next scenario over, let's make that be 0.1 osmoles per liter. And then the last one over here, let's make that one 0.5 osmoles per liter. And then let's go through what will happen to the water. So with our first one, concentration inside, concentration outside are the same, so we don't really need to move water. Now there are holes or aquaporins here, so you'll have a little bit of water going in, a little bit of water out, but overall we have no net movement. So let's actually kind of break all this down. So what we're first going to describe is your osmotic flow. In this scenario, there is no osmotic flow. I'm saying no net flow. There's a little bit going in, a little bit going out, but overall there's no gain or loss. So what's going to happen to our cell? Well, in this case, the cell will look normal. Not gaining any water, not losing any water. So we have a normal looking cell. Now, we have basically 3 scenarios here, right? We have one where the concentration is the same, one where the concentration is lower, one where the concentration is higher. And so, of course, we can categorize these things. And so what we're going to now work through is what we call tonicity. Tonicity is always describing the ECF. So you're basically talking about what will the extracellular fluid do to the tone or the firmness of your cell. Will it make it stay the same? Will it make it swell? Will it make it shrivel up? So tonicity is going to describe our ECF. So in this case, our ECF, if you compare it to our ICF, is the same. There's no change to our cell. So the root for that is iso. So iso is same, but in this case we call it isotonic because you're describing the extracellular fluid as something that will cause the cell to stay the same. So it'll have the same tone or tension. Okay, so let's go to our second scenario here. We have a higher concentration inside of our cell. So we go back to our rule. Who's crowded? Give them water. So we're going to take the water from the ECF and put it into our ICF. So our osmotic flow is going from extracellular fluid to intracellular fluid. So we're going to have water go in. What will happen to our cell if water goes into it? It's going to expand. And it could expand so much that it would actually blow up. You could actually end up, doing something called lysis. And if it's a red blood cell, we call it hemolyze or hemolysis. All right, so our cell is going to swell, or it actually could disappear. It could burst or lyse. What kind of environment will cause that? Well, one that's lower than the inside. If it's lower than the inside, water is going to go in. And so the root for low or below, we've talked about before, so we have hypo. So hypotonic environments cause the cells to swell up. The trick I use is hypo, swell up like a hippo. So these are the ones that make the cell blow up. Our third scenario that we're going to work with is one where the extracellular fluid has a higher concentration. So if the extracellular fluid has a higher concentration, water is going to leave our cell. And if water exits the cell, we're going from the ICF, intracellular fluid, to the extracellular fluid, or ECF, for our direction of flow. Our cell will shrivel up. When a cell shrivels, we call that crenated. So this cell will look crenated, shriveled up. Environments that cause that are higher in concentration. So the root for when it's higher is hyper. So hypertonic environments cause the cell to shrivel. So the trick I use on that is if you're hyper, you run around a lot, you get skinny. So hypertonic environments causes the cell to get skinny. Now, we haven't talked about penetrators yet. What would happen with a penetrator? So let's kind of make the scenario. So here's it kind of drawn up. So let's say we have some penetrating solute. So since I have 0.6, let's actually kind of just draw this out. 2, 3, 4, 5, 6. And just kind of picture 6 purple dots. So 6 penetrators. Are there any purple dots on the inside? Nope. So if they're penetrators, where are they going to go? They're going to go down their gradient. And so some of those purple dots are going to go in. And so as those purple dots go in, the concentration on the inside is going to keep getting higher. Concentration on the outside is going to keep getting lower. And so in that case, where's water going to go? Well, if the solutes are going in, the water is going to follow it. So anytime you have a penetrating particle, you will have water go in. What will happen to the cell? It's going to swell. So if you have a penetrating solute, solutes are going to penetrate. If solutes go in, water is going to go in. This is always going to be a hypotonic environment. So penetrating solutes are always going to cause it to be a hypotonic environment. Okay, so if we zoom back into our PowerPoint, we have this all in Blackboard, or I have this all in Blackboard for you. To remember, we're talking about the extracellular fluid and how that will affect the volume or the pressure or the tone of the cell based on how water is going to move. You have 3 scenarios. If you put cells in an isotonic environment, you will have no change in tension. If you put them in a hypertonic environment, then the cell will shrivel or crenate. If you put them in a hypotonic environment, then the cell will swell up and it might even burst.